Hi, Shelby. Good morning, Vanessa. Hi, Karen. Good morning, Hannah. Good morning, Jake. So we'll need to be on SPSS this morning, and we'll need to be on Excel. Okay, we've got 8 a.m. So why don't we get started? Good morning, Psych Stats.
Good morning.
All right, well, welcome to 8 a.m. on Thursday of week 9. We are truly in the middle of it. A couple of announcements today. I'm looking forward very much to our tribute to Oliver Sacks, neurologist and writer. That's going to be 4:30 this afternoon. The Nerds will be hosting that. PSYC will be hosting that. DUBS, that's the Denison University Biological Society, and also Outlook. Very interesting issues that Oliver Sacks had with sexual orientation, so it should be a terrific presentation. We hope you can join us today at 4:30, right next door, all the way downstairs in room 115. Hope you can join us at that time. Okay, other things to do. This is now 1 week away from quiz number 3, and so I always like to, at the 1 week mark, announce what's going to be happening on the quiz. And what's happening on this quiz is the same thing that's going to be happening on all the other quizzes. You've seen this slide many times before. This is some general information about the content of the quiz and the context for the quiz and so forth. These are some of the skills to practice and memorize. We're working on one-way ANOVAs as of yesterday, and we'll be doing some factorial ANOVAs today. These are some of the commands that you might be familiar with. You remember doing the T distribution, the T-in distribution, FDist and FN are related to those two. So those are some Excel skills. And we'll be working today in Excel and also in SPSS. Okay? In SPSS, we want you to be able to do all these different kinds of things with ANOVAs. That's this week and Wednesday of next week. And multiple regression we've already finished. And this is just a small list of the things that you learned to do while you were learning about multiple regression. Okay? Also, because the course is cumulative, here's a list of some of the things that you've done it's not an exhaustive list, but a list of some of the things you've done for previous quizzes. Okay? And this is all available to you on the S drive. So I'll give you some more reminders about this. It's not a lot of points, but it's a way of keeping our skills tuned and distributing our practice across the semester. Okay? All right. Okay. So one other reminder is that tomorrow we'll have one more TED Ed, and that might be the last TED Ed that we have before the quiz. We could have one more for Wednesday, but I think probably not. Maybe we'll save Wednesday just for entirely hands-on practice. And we'll do a lot of that today and some of that tomorrow, but I think we'll need one more TED Ed to do a new topic called orthogonal trend analyses, which I think none of you have done before. It's a little bit tricky, and we'll do that one tomorrow, and I think that'll be our last TED Ed before we get to the quiz, and then also tomorrow I'll hand out a writing prompt, which will be exam 3, and that will take the form of a written essay as we've done in the past. Okay? So coming up on the section 3 assessments for the quiz on the computer and the written assessment. Okay? Any questions about where we're going for the next few days? Okay, why don't we do this? Can you join me back out on Excel? We finished yesterday inside of this Excel exercise, which was a one-way ANOVA. It was a between subjects ANOVA. And again, this is out on the S drive if you go to our resources folder. And within the resources, you'll see that there's the practice sets, and there's a between subjects ANOVA, and we were doing that one and only Excel file there. We were on problem number 1. In the population, all means are equal. That's what we're testing. And we were using basic ratios. So just to get you speaking a little bit this morning at an early hour, can somebody remind us what the basic ratios do for us? Okay, thanks, Melanie.
They help us compute the sums of squares.
Yeah, right. Okay, the basic ratios help us compute the sums of squares. And we had a y, a, and t basic ratio. We won't do that again today. We'll come back to y, a, and t, though, probably tomorrow when we do a manual computation of a factorial ANOVA. So we're still in the one-way world. By the way, what does one-way mean? We have a one-way ANOVA. I mentioned that yesterday. It was a term some of us were not familiar with. A one-way ANOVA. Okay, thanks, Hannah. One independent variable. Okay, now it can have multiple levels. The example that we're using here actually has 3 groups. This is a between group analysis. We have 3 different groups. But you might think of this as having 0, 1, and 2 milligrams of Prozac, or if you prefer, 1, 2, and 3 milligrams of Prozac. It's done in a between groups manner, but we have 3 levels rather than 2. But it's still one variable, and our variable in that hypothetical would be Prozac level. Okay? Now what we could do is we could have Prozac level by exercise group, right? And we could have 3 different levels of exercise, and then we could have 3 different flavors of Prozac. There's 3 different levels of Prozac, 3 different levels of exercise, and we'd have a 2-way analysis. It happened to be a 3 by 3, but we would have 3 levels of each of those 2 variables. But here we're still in the one-way world, and as we mentioned a moment ago, we used y, a, and t to help us get these sums of squares in our F summary table. Who's okay with all of that? Is that sounding familiar? Okay. So we did this little mixing and matching, and I promise you will never have to memorize how to mix and match those. That will be handed to you for Thursday's quiz. It gives you the sum of squares. We divide the sum of squares by degree of freedom, and that stands for what? MN? This column is called the mean square, okay? And we said it was synonymous with some other word that we learned earlier. Variance, okay? These are variances, right? So we have an analysis of variance in an ANOVA. And actually, it's an analysis of 2 variances. It's the mean square between over mean square within. Okay, so that's an important way of partitioning the variability. We have this total variability, and we can say a certain amount is between, a certain amount is within. We call the within component the error term. We did this yesterday. We're having larger or smaller error bars. Okay, so that's where we were yesterday. We computed an F ratio. And the F ratio that we had last time was a little bit less than 1. So on this graph, which is the distribution of all possible Fs, we got only about this far. And you would expect to get that far by chance, typically. Okay, we need to get all the way out here in order for us to claim that we have statistical significance. So we'd need to be at this point where we would be cutting the distribution such that 95% is this way, 5% is that way. Where did we actually cut the distribution? Okay. We know that we're right about here. Can somebody help us out with what those numbers might be? What fraction winds up over on this side and what fraction winds up over on that side? Given our empirically observed F value up there. I'm giving you a hint by pointing to that screen. So we're at 0.95. What fraction is this way? What fraction is that way? If we had been right here, what fraction, or what proportion is this way? What proportion is that way? This way we have 0.05. This way we have 0.95. Okay. If we're right here, some idea about what that is? The column next to the F ratio might be helpful. How many people are not? Yeah, please go ahead. Yeah, okay. So what fraction do we have to the? So here we are. Here's our line. We empirically observe this F value. Who's okay with that? Okay. And we want to know what fraction of the distribution is this way, or what proportion is this way, what proportion is that way. Any ideas? Okay. 41% is that way, and 60% is that way. All right. Let's see if we can do that again. Let's say that we hadn't got an F that was equal to 0.95. Let's say that we got an F up here, and we got an F that was right on this. I'll make up a number. We'll say it's 3.2. Okay? Say our F value is 3.2. 5% is this way, 95% is that way. Who's okay with that? Okay. If I have some smaller value of f, okay, then I'm going to have some larger fraction on that side and some smaller fraction than 0.95 on that side. Okay, if that's working for us. What we empirically observed was right here. The critical alpha level, 0.05, would be over here. The observed alpha level, the sig value, was 0.41. That tells us that we landed over here. We'd have a 41% chance of getting an f value that big or bigger just by chance, is what's going on there. This might be a little bit clearer, too, if we do one more trick. What XL command did we use to get that one? fdist, okay? And if you're not sure about that, you can click on it. And people have that one up. You can click on that and see it's fdist, okay? Let's do one other one, okay? This is a little bit tricky. Okay? Let's do fcrit. Let's find the critical value of f. Does anybody know which command we would use for that to get the critical value? Inv, okay? Equals finv, okay? And we want to find this value. We want to find the f statistic that would land right here and cut the distribution such that 5% is that way and 95% is that way. Okay? So we'll put in 0.05 as we typically do. The degrees of freedom we can borrow from the neighboring columns. There's a 2. Here's a 9. Okay? Okay. And I had guessed it might be around 3.2 or something. It's about 4.25. So we'll put that number in. So if we were at an f value of 4.25, and I'll put this in black, that would cut the distribution in such a way that 5% is over here and 95% is over there. Instead, we're cutting the distribution right here at this dotted line, 0.95, and that's leaving, according to this, 41% of the distribution over here, and is that 59% over that way? Is that about right? Yeah. How many people are following that? How people are not sure that they're following that? It's okay if you're not sure. All right. All right. So we have the fdist and the finv kind of commands. I'd like to do something else. We've talked about the challenges associated with hypothesis testing. What were some of the challenges? In fact, we had a whole essay on that. Whenever we're engaged in hypothesis testing, we're rejecting or retaining the null hypothesis, and there's a really large criticism about that. Anybody remember what that was? Null hypothesis testing, there's trouble in paradise, the paradise of null hypothesis testing. What was that problem? Okay, thanks, Hannah.
If you have the same numbers but there's bigger sample size, then it's going to be significant where that's not a sample size.
Yeah, right, okay. So the idea about whether we're going to reject the null hypothesis or not, whether we reach the magic 0.05 alpha level or not, is completely dependent on sample size, or at least it can depend on sample size, okay? And as our sample sizes get larger, actually, what we tend to do is shrink down our error bars. Okay, so sometimes you might have a little bit of a difference, and if you shrink the error bars down far enough, you could say that's statistically significant. So we said what we might want to do instead is measure effect size. What are some measures that we have of effect size? Does anybody recall? Yeah.
Cohen's d.
Cohen's d is a very good measure of effect size. Something else? What else is a measure of effect size? Yeah, thanks. Eta squared, right, or a partial eta squared, either of those, which would be like an r squared. So what I'd like to do now is why don't we add to this f table, we've done all the basic f computations, now we've put it into context. We figured out where the f value actually is and how much of the distribution is on that side, how much of the distribution is on that side. Why don't we see if we can get a measure of effect size? Why don't we do something like an eta squared? So over here, I'm going to put an eta squared. And we had in one of our PowerPoints fairly recently an indication of how we compute the eta squared, but I don't think I made it a TED-Ed question. Okay? Does anybody know or have an idea about how you might compute the eta squared? Okay, which is the proportion of variance explained. Some idea about that? Okay. Would not be entirely obvious. It's going to be a ratio, just like everything else in this class is a ratio. And we'll do it this way. We're going to see how much of the variance is attributed to our between-group manipulation. In this case, we'll think of it as the Prozac manipulation, 1, 2, or 3 milligrams of Prozac. We'll pretend that this group got 1, that group got 2, and that group got 3 milligrams of Prozac. And we have some variability that is attributed to that. And then we can think about the total variability as the sum of this plus this. So let's see if we can begin to build that. We'll say that eta squared is equal to, okay, the variance, or its indication of variance, that we have attributed to the between group variable, or the between group factor, divided by the total that we have. What fraction of the total SS is that? So that's going to be this guy plus that guy. Okay, let's see if we can do that again. We'll say this plus my neighbor downstairs. And I'll let you hit the enter key. I'll leave that just like that so you can see what I've done here. I've said what fraction of the total SS, the total sum of squares in the entire experiment, is attributable to our between subjects manipulation. So it's that top number over the sum of those two numbers. Who's following that? Does that make sense? Okay, it's a fairly simple ratio. Okay, and what did you get? 0.17 and some change. Okay. All right, so that's all working pretty well. So now we have a lot of information here. We have information about the degrees of freedom and the actual F ratio, where that sits in the range of all possible F ratios, how it cuts the distribution, and how far away we are from a critical value. And we also know how much of the variance we're explaining. We're explaining about 18%, 17.5%. Yeah? So far, so good? Okay, why don't we see if we can do this. I wonder if we can now take this exact same layout and move it into SPSS. Okay, so we'll make a conversion here from Excel over to SPSS, and we'll see if we can corroborate these numbers. Okay, so if you'll join me in opening up a tabula rasa inside of SPSS, let's think about what we might want to have here as our variables. Okay, so can somebody think about what variables we might want to put in here? We're going to run exactly the same analysis, same one-way analysis. We have to get some variables entered, and then we'll plop in some data with a cut and paste. Let's take a look at our Excel spreadsheet and see what we have here. Here we have 3 groups. So far, so good? So why don't we have a group variable? Okay, we'll have a group variable. And we might even have a participant variable. It's not really a variable, but some way of listing who the individuals are. And then, of course, we have the scores for any given person. So we have 12 people here in these different groups, 4 in each of the 3 groups. Okay, so it looks like we're going to have some kind of a score to capture what these numbers are. We'll have some kind of group designation. We might also have a participant ID. Okay, so let's go over here to variable view, and let me just make sure by a show of hands that we all have SPSS up. Who has that up? Okay. All right, so why don't we do this? Why don't we create a placeholder so that we can label each of our participants, and we'll call this participant ID. It's all continuous. Okay. And we're going to make that one, if you'll click over here with me, I'm going to go to type, and I'm going to make that a string variable so that I can enter some numeric or alphanumeric phrases, like I can call the first participant P1, P2, P3, and so on down the line. Okay. We also said that we had a group variable. Okay, we're going to have 3 levels of that. And then we have some kind of dependent variable. It's a score of some variety. And we'll leave it generically as score. Okay? And now if you'll join me in clicking over here, you've got participant ID, group, and score. How many people have that much? Yeah? Okay, is that working for us? Vanessa, how are you doing? Did that work? Yeah, okay, real good. Why don't we drop straight on down the line here? Why don't we put in P1 through P12 to correspond to our 12 participants? Okay. This would be something akin to what you would do in an actual experiment. Okay, and we probably could fill these in right away, these group designations, but maybe we can have Excel do that. So let me just check in and see how many people have those 12 P's there, the 12 different participants. Yeah, that's working for us. Okay, if you'll join me, we'll go back over to Excel, and we'll see how we might reorganize the data just a little bit. So I'm going to grab these 12 items. I'm way up top in Excel. Okay, And I'm going to grab the ones that are not shown in yellow. I'm going to do a Control-C so I get the ring around the rosy going. And I'm going to make a copy of these just a little bit over to the side. I'm going to go over maybe just this far so it looks like a tabula rasa. And I'll paste those in. Remember that this was group 1, group 2, and group 3. Who's got that so far? Did I lose anybody there? Okay. Can you grab this second group, if you will, and put it underneath the first group? Right? And we're going to take the third group and put it underneath the second group. So now we've put them into a columnar manner rather than having them distributed across the different, having them distributed horizontally. Does that work for us? Now we have a list of 12 numbers. And these first 4, you might remember, what was their group number? Real loud? 1? Okay, so let's put in 1 4 times. This was a group 1. 1, 1, 1. Then what was the next group? Group 2. 1, excuse me, 2, 2, 2, 2. And the last group was group 3. Okay? So now we have a group for each of these participants, and we have their score, and that matches the 2 variables that we had a little while ago. Who's following that? Did I lose anybody there? Okay. Let me make sure I put them in the right order. So right now I have group on the left, and I have score on the right. Is that what I did in SPSS? I might have to move those around. It is group and score. Okay. So what we can do then is go over to what we just had in Excel, highlight that, do a Control-C, and get the ring around the rosy going, and we can plop those in to SPSS. Okay, and now we've taken some different looking data structures. We had something that looked like group 1, group 2, group 3 inside of Excel, and now we have those nicely inside of SPSS. Who's okay with all of that? Okay. Okay, so we had a little while ago done the manual computation of the ANOVA. We used basic ratios to get the sums of squares. Once we had the sums of squares, we were home free. We moved all the way across the F table, and we even did such things as compute eta squared, and we figured out how we're going to cut this distribution, the empirically observed alpha level, and all that good stuff. Let's see if we can now just recreate some of that inside of SPSS. There are at least 2 ways of doing a one-way ANOVA in SPSS. Why don't we see if we can do them both? I think the second way is actually quite a bit more helpful, but anybody want to help us out with how we might get this started? Give you a clue. Analysis of variance is an analysis. Analyze. All right. What do you think? Compare means is a really good one, but let's do that, okay? And that was that you, Shelby? Okay, that's perfect because we are comparing the means to each other. So that's very logical. So far it seems like they're with us. And look, we get a one-way. We only have one factor, and that happens to be the PSYC factor, which comes in 3 flavors, 1, 2, and 3 milligrams. Okay, so we'll click on that. Okay, and our dependent variable is which one? Which one's our dependent variable? Score. Okay, there we go. And our factor, I wish they could have called it an IV, is going to be that. Okay, so we've got that much going. Who's all right with all of that? Yeah? Okay, we also introduced in the PowerPoints anyway some post hoc tests, and we had some questions about the post hoc tests. Who remembers reading those TED Ed questions? Okay, let's go to post hoc, and we have a lot of choices here. Let's just take some of them. Why don't we take a peek maybe at Chefet, and why don't we take a peek at Tukey, and there are different Tukeys. We'll take the top Tukey, and Dunnett, just to get some variety going on there. We will come back. We'll spend a lot of time on Bonferroni in sessions to come, but that will keep us busy for right now. Okay. Let's see what else we have. Options, anything good here? Why don't we take some descriptives? And why don't we take some homogeneity of variance tests? What's that one called, by the way? Can we all yell it out? The name of that homogeneity test? Starts with an L. Levine, okay, so maybe we haven't seen that in a while. So we'll take the Levine's test, we'll take some post hoc tests. That'll be enough to keep us busy. Okay, who's all right with all of that? Okay. We'll say okay. All right, we get our first output. So here are the descriptives. We have the 3 different groups, and we have n equals 4 in each of those. Standard deviation, standard error, confidence intervals, minimum, maximum. We've done all that before. Okay, nothing particularly new. Okay. Can somebody help us out with what we're going to do on this box, the homogeneity of variance test by Levine? Somebody mentioned it in class yesterday. Maybe you can help us out with the interpretation of that today. Levine statistic, 0.894, degrees of freedom, 219, sig 0.442. What's going on with that? Thank you, Hannah.
I'm looking to see if the variances between these groups are equal.
Are they approximately like this, or if you will, approximately like that, which is still cool, but they can't be like that, okay? One is a lot smaller than another. And if we just eyeball the variances, we can take a look at the standard deviations. They're not the same, but Levine's test is telling us they're relevantly similar to each other. If that had been a larger statistic, the sig value would be much smaller. At some point, it would get down to 0.05, and we could reject the equal variance assumption, and that would be a shame, because if we had to reject the equal variance assumption, we'd have to do some other kind of a test. But we can now assume equal variance because the variances are not significantly different from each other. Who's following that? Is anybody lost on it? That'll be important. We're going to come back to that many, many times. And actually, we should have done something like that in the world of multiple regression, but we had other fish to fry. So now we're going to look at it very carefully here. Okay. This should look very familiar. How many people recognize this? Yep, that's looking pretty good. Okay, so that's as far as we got. And you stay right there. I'm going to flip back over, and we'll take a look at our degrees of freedom, sums of squares, mean square. I'm going to flip back over, and we'll see. That's where we were a minute ago. And that's where we ended yesterday's session, right? We had done these numbers. Okay? Maybe I can put them in red just for a moment. Kind of take a mental picture of that. We'll flip back over to SPSS. Okay, and here we are. And hopefully those numbers look really good. Okay? So it's nice to see that SPSS gets it right. Okay? All right, they're able to corroborate all of that. Okay? And so if we were to write the APA-style statistic for this, we would say F 2 and 9 is equal to 0.959, and the p-value there is 0.419. Okay? So we could have gotten a an F value that large or larger 41% of the time, nowhere near the 0.05, and we're going to reject the null. We're going to retain the null hypothesis. Excuse me. Okay, let's drop down to this, and we'll see if we get a post hoc view here. How many people do have the post hocs showing? Yeah? Okay. All right, I wonder if somebody can walk us through what's going on in the Tukey post hoc. How many people find that intuitive? How many people don't find that intuitive? How many people aren't voting? Okay, like we need to wake up. All right. How many people are okay with this? They think they understand that? How many people are not sure that they understand that? That's okay. We're not sure. Thank you for saying so. Okay, so what goes on in the post hoc test is the following. We recognize that in the ANOVA, we have a theme song, which is one of these things that's not like the others. We now have something like 3 groups, and it could be the case that we had a significant difference. If we did, we'd have to figure out where those differences are, and we would use the post hoc to make the pairwise comparisons. And so what's going on here is, in this particular post hoc comparison, they're comparing 2 groups at a time. We'll call one of them I, we'll call another one of them J. And in this first analysis, we're going to compare group 1 to group 2, and we're going to get a different score there, a standard error, and a significance on that difference. It's nowhere near 0.5. So group 1 is not significantly different from group 2. Okay? Group 1 is not significantly different from group 3. Group 2 is not significantly different from group 3 because we're getting sig values there that are always greater than 0.05. Who's following that? Is that working for us? Okay. Now, this, again, is really playing 2 roles for us, which you might remember from research methods, and that is that the post hoc tests help us to pinpoint where the differences might be. Okay? So far, so good? Is that working for us? They also make an adjustment. They make an adjustment for cumulative type 1 error, which was something that was introduced in the PowerPoints but wasn't mentioned here. Can somebody help us out with that idea? Cumulative type 1 error, sometimes called family-wise type 1 error. No? Okay, thanks.
Okay, so I think it has to do with like you're testing a bunch of different times.
Okay.
All of those errors add up to like one big error.
Okay, right, so you're testing many, many times, and this is rearing its head for the very first time here in the world of ANOVA, because typically we just have 2 in a t-test, 2 means that we're comparing to each other, but in ANOVA we can have any number of them. So you can imagine that maybe there's really no effect for your manipulation, okay? But if you have lots and lots and lots of groups, just by chance, every once in a while the 2 are going to differ from each other rather markedly, just by chance. So what you might need to do is correct for that. You might say, well, yeah, you do have a statistically significant effect, but you also got, if you will, many, many lottery tickets. And the more lottery tickets you have, the better the chance is that you're going to win the lottery, just by chance. Right? So we need to somehow correct for the situation in which you've accumulated this probability for type 1 error. And you've done that by having lots of different groups. Okay? Here's one of the ways of thinking about this. Just so you have some appreciation about how this might work, we have now hard-coded over here in Excel. You don't have to go back to Excel. We've hard-coded all the computations here. And we have these group values. What I could do is I could add something to, I could turn these into random numbers. Like, why don't I do that? I'll make them rand between, we'll say 1 and 50. You don't have to do this with me, but just so you have some idea here. Okay, so that's now a random number. I'll pull it down, I'll pull it over, and now I've done everything the same except I have random numbers rather than the original numbers. Who's okay with that? Okay? If we keep our eye on the p-value, and I keep hitting this, okay, I just hit it one time, and I happen to get lucky. When I randomly generated another set of numbers, I hit the jackpot, and I generated a really fat F ratio. I'm now all the way over here, and I generated a really small p-value just by chance. And because all I used up here were random numbers. Okay? Who's following that? Okay? So I did it one more time, and all of a sudden I'm significant. So we have to control for that accumulation of random probabilities. If I hit the F9 key one more time, it'll probably go away. Why don't you keep your eye on the p-value here? Right? And most of the time it's going to be greater than 0.05. But definitionally, 5% of the time, it'll be less than 0.05. Okay, so I'll try to do it 20 times. We'll see if we get a hit 1 every 20. 1, 2, 3, 4, 5. There it is. Okay, so on the 5th one, it happened to come up less than 0.05. Okay, here's one other guy. I can do this. Equals. Can somebody help me out with the if syntax? Anybody remember how that goes? Equals. I'll do it out loud. If this guy is less than 0.05, okay? If that's true, why don't I say sig? Otherwise, I'll say nothing, right? And you won't have to do this on a test, right? But I can hold this down now, and every once in a while I see sig go flashing in the center there, okay? That gives you some idea about this notion of cumulative type 1 error that Gabby has correctly described. As we're running more and more and more tests, we're going to get these things even if you really don't have an effect up here. All you have is random numbers. Okay? So we have to somehow control for that. And we have to have a more and more stringent control the more lottery tickets we've purchased, the more tests we've run. So going back over to here where you are, in SPSS, we can say that the 2 key makes some kind of an adjustment. It's actually going to look at the original alpha value that it computes, and it's going to jack it up a little bit and say, well, you've got to be a little bit higher than the regular 0.05 for us to give you statistical significance. Chef A makes also the same kind of comparisons, but probably jacks that number up even further. Okay, as you can see here. See if you can notice this. Let's compare 1 to 2, and we'll look at the sig value for the 2 key. And do we see that it's 0.391? And people are seeing that? Okay. All right, so that's pretty far away from 0.05. If we had done the same thing in Chef A, we're going to compare 1 to 2, we're at 0.423. Chef A imposes an even stricter penalty on you for cumulative type 1 error. It says it's going to move you even further away from this goal line. Okay? 2 key is going to move you back a little bit. Chef A is going to move you back even further. Chef A is considered a more conservative correction because you'd have to have a really, really large effect in order to reach the critical value here under the Chef A correction. Who's all right with that? Yeah? Okay. So, by the way, what the Chef A does is it controls for these comparisons, 1 to 2, 1 to 3, 2 to 3. It also compares for what we might call complex comparisons. There's another family of comparisons where you can combine 1 and 2 into a new group, okay, the combined 1 and 2, and compare that to 3. you can combine 2 and 3 into one group and compare that combination to 1, and you can combine 1 and 3 into its own group and compare that to. Chaffee corrects for all of those possibilities. And because it makes that many corrections, it moves you back that much further. Okay? It imposes that much more of a penalty. All right, so that's our little introduction to post hoc tests. And they rear their heads for the first time once we do ANOVAs, because now all of a sudden we have more than a two-group comparison. We have lots of different comparisons, and we have this accumulation effect going on. Okay? Questions on any of that? Okay, so just to have an interim summary here, we've computed the F statistics using our basic ratios. Okay, we've partitioned the variability, mean square between over mean square within. We found an F ratio. We put it into some kind of context relative to other F statistics. We figured out how much of the variance we're explaining, and it was a relatively modest 17% or so, and we'll come back to that in a moment. And then we also did our post hoc analyses. Okay? And we did this all because Shelby got it right and said analyze, and we're comparing means. Okay? There's another way to do this too. Does anybody maybe recall a different way of running an ANOVA that I'd like to do now for you? And this one might actually be more helpful. It'll be a little bit redundant, but it will give us some other information that we can't get through Excel's one-way ANOVA mechanism. Yeah, thanks. Okay, thank you. So, and you might jot these steps down. Okay, so this is the sequence that we're going to do. We're going to analyze. We're going to go to general linear model, and I apologize for this. It's general linear model, and it is not generalized linear model, and they're right next to each other. Right, so it would be really easy to make a finger error there. Sometimes SPSS isn't as friendly as it might have been, but it's going to be general linear model. Okay, and here we're going to come to a fork in the road. Today we're going to be using the univariate option because the one variable that we're looking at happens to be between subjects. If you're doing some kind of a design that has a repeated measures factor, you would go to repeated measures. Okay? If you have a mixed design, where some of your variables are administered between subjects and some are administered within subjects, we would still go to repeated measures. We use the univariate variety only when we have an entirely between subjects analysis going on. And that's what we have here. We have just one factor, and it happens to be entirely between subjects, so we're going to go univariate. Okay? So that sequence is analyze, general linear model, univariate, because it's all one. Okay? Who's all right with that? That work for us? Okay. Let's see if we can do this now. Our dependent variable, can you yell out it again? Score? Okay, why don't we slide that one over? And this is just a tad confusing. Really, for the rest of the semester, we're going to be using fixed factors. Okay? That is to say that we've put our PSYC necessarily at 1, and at 2, and at 3, and it's fixed at those levels. We don't have random values of, we could have had random values of Prozac, where we could have a 0.93 milligram and a 1.72 milligrams. We could have them entirely randomly, but we fixed them all at 3 particular levels. Okay? So we're going to call this independent variable now a fixed factor, because we have them in 3 groups that are treated differently from each other, but within a group, everybody's treated at a fixed level of that variable. Who's okay with that? Okay? All right, so a couple of other things to click on. Why don't we do this? Just to remind us, why don't we get the same business going with post hoc tests? And we'll do this on group. Okay? And why don't we take the same ones again? It was Chaffee, it was this Tukey, and it was Dunnett. We'll come back to Bonferroni when we do a within subject analysis at some point. Okay? Click on continue. Okay, and then the other thing we want to do is options. Okay, here's where it gets a little bit interesting. Why don't we take both of these, the group and the overall, and we'll get the means for those. So we're going to slide those over. And there are 4 other boxes I'd like you to check on this options menu. It's the first 3 over here. We want to get the descriptives. We want to get some estimates of effect size, which we didn't get a moment ago on the simple compare means menu. And we'll get the observed power, the probability of finding an effect if it's there. Okay. We also have to click on homogeneity tests to pull out the Levene and make sure that our assumptions are okay. So we've got those 4 boxes. It's 3 in a row, and then this guy over here, and we'll get the means on all of that. We also clicked on the post hoc tests, and when you're set, you can let it rip by clicking on OK. It will take just a moment for that to come out. And we go to the univariate analysis that we have here. How many people have that? Okay, we're doing okay on that. All right, so what we have cooking there are group way up top. We have 3 groups, and there are 4 persons in each of those groups. And you can see that we get some descriptive statistics here. We've seen that once before. Here's Levine. It's exactly the same thing we did a moment ago. This is our test of equal variance. And we have a sig value that says don't reject, but rather retain the equal variance assumption. Okay? And now we get the F output kind of like what we had before, but we're also getting a couple of other boxes that we didn't get the last time. And that's why I prefer to use this sequence of clicks inside of SPSS, because it's more informative. It gives us information about partial eta squared and observed power that we weren't getting just a little while ago. Something that you will not need to deal with this semester is the non-centrality parameter. It's something that is used in the computation of observed power. We don't need to go there, but we certainly will need this and this. Okay? Okay, how many people think that number looks familiar? 1.76? And why are some people shaking their heads yes? Or where did we see that before? Okay, when we did the partial eta a moment ago, and the way that we did that, just to remind you, was we said, well, how much of the total SS is going to be, and the SS is shown here, is attributable to group, and how much is attributable to error and the total, and we found that proportion is 1.76. So it's nice to see SPSS has gotten that number right again. This can be a little bit busy. What we really want here is just the group bit. Right? We want that center item, and here's the error. The intercept and the corrected model are things we don't need to be looking at. Okay, so that's just about everything that we have right there. Okay, and here we now have the same comparisons that we had just a little while ago. You can disregard the homogeneous subsets. We'll just take that out so it doesn't confuse us. We might spend some time on that later this semester, but that's plenty for right now. Okay, so now we've got lots of information for a full APA style, an APA style statement with the F and the degrees of freedom and indexes of observed power, and also of proportion of variance explained or effect size. Okay. Any questions on any of that? No? Okay. Okay. A couple of ways we can go. We have about 10 minutes. I really do want to spend some time introducing the difficult topic of interactions in factorial design. So let's move over now to a conversation on factorial designs, and we'll build on what we're doing here in the one-way analysis. We'll now go to a two-way analysis, and the simplest kind of factorial design that we can have is a 2x2. Okay? And in 2x2, we have 2 levels of factor A, and we have 2 levels of factor B. Right? And that's the simplest type that we can have in a so-called complex or factorial design. Okay? All right, so let's go to something like this. And people were drawing all kinds of graphs. We have lots of different possibilities. We really want you to become very comfortable in generating these factorial graphs. So why don't I have you walk me through a few of these. Okay. So these are all going to be 2x2s, and we have factor A here. We might call this A1 and A2. This is some kind of dependent variable. Okay. And this will be 0, so we'll make this 1, 5, and 9, as I alluded to as we were leaving yesterday. And we have all different ways that we can go with this. I'll take this thing away just for the moment. But you can imagine that you can have 3 different possible effects: factor A, factor B, and the A by B interaction. Okay. Here's factor A. And we're going to parameterize factor B, and here's A by B. Okay. Here's A by B. And we'll do this, I think the convention, you can remind me, something like we used a closed circle, I think, for B1. Is that right? And we might have used an X for B2. Does that sound about right? Yeah? Okay. All right. And we can come over here and we can randomly put check marks in all 3 of these categories or 2 of them, and then say we want to be able to draw a graph that's consistent with what we have over here. Okay? So let's try something like, let's just start out simple. Okay? Let's make factor A significant. Okay? And factor B and the A by B interaction can be non-significant. Okay? So does somebody want to tell me how I might get this graph going? it's okay if you want to click through your TED eds and maybe look for one of those. One of those questions was probably, I think I got every possible combination. I think I had to do 8 of these, and there are 8 combinations, I think, of turning these things on or off with a check mark. In the interest of time, why don't we think about it this way? If you're telling me that factor A is significant, what you're really telling me is that on average, factor level A1 differs in its mean than level A2. There's going to be a mean difference. And it might look like this. Right? That's A1 is bigger than A2, or it might look like that, but there's going to be a difference. Who's following that? Okay? We're also saying that factor B isn't really doing anything for us. It's non-significant, and the A by B interaction is going to be non-significant. Okay? So I wonder if this might work. Why don't I start out with B1? I'll put it up here. And I'm going to take now B1 and I'll put it down here. Okay? So I've taken B1 and I've measured B1 at both the first and second levels of factor A. Is that working for us? Okay. And I can do the same thing for B2, and just coincidentally, maybe it's going to be just like this and just like that. Okay? So now, if I connect those with a line graph, sorry that my X looks a little bit funny there, but I think you get the idea, and that is that A1 has a higher mean than A2, so I have a significant mean effective A. People okay with that? By the way, what is my mean at A1? Can we yell it out? 9. What is my mean at A2? It's going to be, oh, I'm sorry, I should have put that at 1. Okay, I overshot a little bit. Got a little carried away this morning, okay? We'll pretend that's at 1 if you'll bear with me, okay? What is my mean score? If we can pretend that those are 9s and 1s, that's what I was shooting for. What is my mean score for B1? 5, okay? And that's why we have this number, okay? Because I have, here's a 9, here's a 1. 9 and 1 add 2. And we divide 10 by the 2 scores that we have. 5, okay? So B1 is right here. How about B2? Okay, so B1 is 5, B2 is 5. Are those different from each other? So B2 is non-significant. Doesn't get a check mark. Is that people following that? Okay. Those are not crisscrossing, right? Here's a crossover interaction, right? These are perfectly parallel. So we have absolutely no evidence whatsoever for an A by B interaction. Is that right? Okay. So we okay with that one? All right, really good. Okay, why don't we do a few other combinations here? Okay. Why don't we start out relatively slowly? Why don't we change it around to this one? And now I'll let you direct me. I won't put you on the spot and have you come up here. Some idea about what this might look like? Anybody want to help me out? I always encourage you to take advantage of 9s and 1s on these graphs. Thank you, Mel.
So I have like the line with like the circle's both at 1.
Circles both at 1. Okay, I'm going to get, here's a circle. So you're plotting B1, and I'll connect those in my line graph.
And then I have the X's both at 9.
Thank you. Perfect. That's exactly what I'm looking for, okay? Okay, so let's take a look at Melanie's B2. Those seem to be at about 9, okay? And Melanie's B1 seem to be at 1. And so we're getting a difference between B1 and B2. So her B factor is significant, right? Okay. And if we took a mean between this one and this one at A1, we're getting that, and we're getting that. So A1 has a mean of 5, A2 has a mean of 5. A's are non-significant. They're perfectly parallel. We're not getting an interaction. Who's okay with that? Is that working for us? Okay. All right, how are we doing on time? We have time for a couple more of these, okay, but I'd like you to really be able to master these. And sometimes they're a little bit tricky, okay? Why don't we try some combinations? Let's try something like, let's turn on the interaction, because we haven't done an interaction yet. And why don't we turn on, ooh, this is kind of interesting. I think this sometimes gets some folks. Okay, anybody want to help us out with that combination? So factor B is significant. A by B is significant, but factor A has gotten nothing. Okay. Okay, thank you, Victoria.
So, I had my first A, B dot at 9.
At 9.
And then the second one at 5.
Yeah, the second B dot is it?
5, yeah.
Okay, is this what you did here? Okay.
And then I had the B2F A1 at 1.
Did I do that okay?
Yeah.
Okay.
And then the second one at 5.
At 5. Wow, look at this. I think that's perfect. Okay, so let's see what's going on here. First, are we agreed that these circles have a higher mean than do these x's? Is that working for us? Yep. These circles would average out to halfway between 9 and 5, which is 7. These circles, the circles would average out to that. The x's would average out to halfway between 5 and 1, which is 3. So Victoria's got a 7 versus a 3. On her B factor, she's completely satisfied this. Good shooting. Are we agreed that those are not parallel? They're beginning to intersect? Yeah. So she's satisfied this. Okay. And then if we take a look at factor A, clearly the mean here is 5 at level A2, and halfway between 9 and 1 is 5. That's perfect. Okay. But it could have gone the other way. She could have had, this is almost forming, if you will, a greater than sign. Okay. A less than sign would have done the same trick. Okay. All right. Questions about that? Okay. There's a couple of other combinations I'd like to do. Why don't we distribute our practice in time, and we'll do this again tomorrow morning. Okay. So look forward to that. We have one other TED Ed going on tonight. And when we come back tomorrow, we'll finish this off, and then we'll do some hands-on computation for factorial ANOVA. Hope to see you tonight at 4:30 in the Burton Morgan Lecture Hall, where we will talk about Oliver Sacks' life and work. See you soon.